Okay, when we look at projectiles, we know the motion of a projectile. So, for instance, we looked at Wile E. Coyote, we know that that is not what he does, is straight down. The path is a projectile. So when we look at that, what we have to realize is both x and y components to this. And when we launch an object horizontally like this, all we are giving it is motion in the x direction. Now, last chapter we were a little, it didn't really matter if you called it x or y, it was displacement. But now what we're going to be very specific, is it x or is it y? So we know x is horizontal, y is vertical. So if I launch something with a certain velocity, I'm giving it a v sub x. I'm not giving it a v sub y. Now, of course, as you know, the instant it leaves the cliff here, acceleration being negative 9.8 will accelerate it toward the Earth, and it will give a v sub y. So the instant you leave here, you will have a v sub y. And notice what these velocity vectors are doing as you go down. It's very important to understand this picture to understand the whole concept behind this. What's happening here is that the y's, look at the red vector, the purple, and the blue, and the green get larger and larger and larger. So whether these were velocity or displacement, you can see that this is increasing exponentially because of the acceleration due to gravity in the y direction. In the x direction, we've got nothing. We shoot it off with something or kick it off or something like that. We give it a velocity, but there's nothing accelerating it. There's not an engine attached to it, propelling it forward or accelerating it forward. We're going to ignore air resistance, which would slow it down. Basically there's nothing in the x direction that would cause us to use a kinematic to change the velocity. And so you do notice that's here. You've got x and x and x and x and x, and it stays the same. The only thing that changes is the y. And so that's really, really important to note. Now, the other thing that's important to note is what if I wanted the actual, now it's very hard to draw an instantaneous on this, a tangent curve and have you see it. So I want you to just kind of take a look. What would I do if I wanted the instantaneous velocity, maybe the final velocity, or even maybe a velocity right here or right here? What would I do? Well, I would take the slope, but what I need to do is do a v sub x and a v sub y. I need both of those components, and then what I would do to find the actual instantaneous velocity, maybe it's the final, maybe it's the middle, it doesn't matter, but whatever point, you're going to want to find the v sub x at that point, and that's not going to change, is it? So that's easy. Whatever it started with, it'll end with, okay? And then you're going to want to find the v sub y, and that, of course, you're going to use kinematics that you've used, a lot, and then you'll find the actual instantaneous velocity. So, taking a look at kinematics in the x and y direction. What I'd like to do is kind of take a look at these. These are the same kinematics you've been using, but a lot of times, if these are projectiles, we don't accelerate, and so we don't even need those. Okay. You could obviously do problems where you have an engine attached and it is accelerating it in the x direction. Or you could have a car rounding a corner and you'd want to know both its x and y components. So there are certainly problems that you could incorporate both of those. Usually for projectiles, well, right now for projectiles, what we're going to do is say v sub x is constant. Whatever we give it initially, we'll keep through the whole thing, neglecting air resistance. And it's y that is going to change because of the acceleration due to gravity. Now, in quite a few of these, though, there is no y initial velocity. It's just being launched horizontally. It's being given an x velocity, so we're not going to have an initial y velocity. So it actually makes these a pretty easy, oops, I don't know what happened there. This is actually supposed to be 2ay. That didn't, well, this, okay, I know what happened. I got cut off there. But this is 2ay, and then you don't have an initial. So I don't know why that didn't get on there. But so these are going to be the formulas that we use without using any kinematics for the x and using them just for the y's, and realizing that our initial y velocity for things that are launched horizontally anyway, we will not have an initial y. Now the next section we are going to launch them at an angle, so we're going to have to put that back in. Okay, but for right now, let's kind of simplify everything down. And we've got v sub y equals a y times t. Those should be subscripts. So a, the acceleration in the y direction, the velocity in the y direction, the acceleration in the y direction times t squared. When it converts from Dropbox, it doesn't do the subscripts. This is basically those equations without the v sub naught. And this is just dimensional analysis because v sub x is going to stay constant if we ignore air resistance. And I can find the distance by simply taking the velocity times the time. So let's take a look at an example. Person jumps from a plane moving 22.5 meters per second east. And so I'm going to draw a very bad plane here. And here's the person, maybe it's a stunt person, and they're jumping from the plane. Well, now this plane is going at 22.5 meters per second. So of course the person is going at 22.5 meters per second. And they're 10 meters up. And there's a swimming pool over here that the person is going to jump out, and if all goes perfectly, okay, that was not the greatest projectile launched parabola, but there we go. It's going to land in the pool, okay? So we're going to just go ahead and use this to find how far we should drop the person. So how far out before the plane gets to the pool should the person jump out of the plane, do this nice little parabola into the pool? All right, so the first thing we have is we have our y, right? Negative 10. We have our a sub y, negative 9.8. We have, let's see, we're looking for x. We have our v sub naught in the x direction, which is 22.5. Okay, we have no v sub y initially, v sub naught y initially. This instant he steps out of the plane, we'll have it, but we don't have it right now. So just due to limitations here, I'm going to erase that little path. You kind of get the path he's going to take. Okay, and we'll just go ahead and do the problem. The first thing we could solve for is we could say, well, how much time is this going to take? By taking v sub naught x times time. And that would give us our x, but we don't have the time. So let's go back to our kinematic and go 1/2 at squared. Okay, and we're going to plug in negative 10 and negative 9.8 and t squared, and we come up with a time of 1.43 seconds. Okay, so the time that it should take for this person to go from here to the pool, the little projectile, is 1.43 seconds. All right, well, what I'm going to do is bring that right back up there, and we have to also realize that v sub naught x does not change. It stays constant. We ignore air resistance, so we can go back up there. And so what basically is going to happen here is we are going to get, that should be equals, we're going to take v sub naught, 22.5, we're going to multiply it by 1.43, and we're going to get an answer of 32 meters. X should be 32 meters away from the pool. He should step out, do this parabola, and land in the pool. Now, at which velocity will this land? Okay, well, I'm going to have to erase a little bit of stuff here and kind of have all that information. You can always switch back in the video if you need to. All right, the first thing that we need to realize is that the velocity in the x direction is not going to change. So if we ignore air resistance, and so what I'm going to say is basically when this person lands, his v sub x is going to be 22.5 meters per second because it doesn't change. Now the v sub y is going to be equal to a times the time. So go back and take a look. That's our simplest kinematic, just a times t, to find our y velocity, and so we get negative 14 meters per second. So to get the actual instantaneous velocity like I did in the last one, I'm going to have to take 22.5 squared plus negative 14 squared, take the square root, and the instantaneous velocity is going to equal 26.5 meters per second. We're going to do one other problem here before I end the video. And this is we have James Bond. He's on the top of a building. And he is it's a 5-meter distance. And it's negative 30 meters. Wow, I did not draw that to scale. Okay. And he is going to need to jump from here to here, so he can live. And we just wonder what speed, how fast does he need to go to get going there? Okay, so we have y is equal to negative 30. We have x is equal to 5 meters. We have a is negative 9.8 meters per second squared in the y direction. We don't have any x acceleration. James Bond doesn't have like a little pack on his back that will accelerate him. Okay, so again, we're trying to find how fast he needs to run horizontally off. And so what we're looking for is this right here. We're looking at how fast does he have to go horizontally. He's not going to have any y velocity to start. He'll have x velocity. So how fast does that need to be? Well, we have the x, that's 5. We do need, again, to find time. So I'm going to go back and equals 1/2 at squared to find time. Now y will be a negative 30. A will be a negative 9.8 times t squared. So the time will be 2.47 seconds. And then what I'm going to do is put that in there. I'll put the 5 in there, and then 5 divided by 2.47, I get a velocity of 2 meters per second. So James only has to make it 2 meters per second. I think James could probably run that fast off the building. And that ends Projectiles Launch Horizontally.